Do you have an announcement also?
Huh?
Do you have an announcement?
No, we just go. So I don't know because we said that we would do a group picture after your lecture, but Eric Ackermans, I don't know if he will manage to arrive on time. So I will say nothing. Anyways, they need to come to the next section, and if he arrives, we do the lecture. I'm gonna send him a message to say he's coming.
Então, eu só vou preparar pouco. Okay. Boa tarde. Good afternoon. Buenas tardes.
Buenas tardes.
Ja, guten Tag, guten Nachmittag. Bonjour. Você não faz diferença entre tarde e... Okay. Yeah, so let us continue now with optical forces. And now, today I would like to show you how optical forces can be used to cool down atoms to very low temperature, and how to trap atoms using cold forces. So the starting point is again the coupling term of the system Hamiltonian, where you have the Rabi frequency, which depends on the position, which may depend on the position. For example, if you have a light field which is not where the intensity is not homogeneously distributed, for example, a focused laser beam or standing wave, where you have nodes and antinodes. So this is all included in the Rabi frequency. Remember that the square of the Rabi frequency is nothing else than the intensity of the light field, the local intensity of the light field at position R. And then you have this term here, e to the IKR, which will be very important also. It describes a plane wave, so it's a propagation of a plane wave in direction of k. And then you have the photon creation operator with the omega, the frequency of the light, and then you have the atomic stepping down operator, sigma, the Pauli matrix sigma minus, which takes the atom down to the ground state, with the phase, with the omega 0 being the frequency, oscillation frequency of the atom. And of course, you have always to add the complex conjugate in order to have a Hermitian operator. Okay, and formally, all you do now in order to derive the optical forces is to take the gradient of this energy, of this spatially dependent interaction energy, and this will give you the force that acts on the atomic center of mass. Okay. So I've written down here the Hamiltonian. Remember that this plane wave, where is here? The plane wave operator here can be understood as a kick operator, which takes your atomic momentum from momentum p, adding an h bar k unit of photonic recoil, takes it to an atom which moves a little bit faster. Okay, now here I show the calculation. So this is the force, and all I do is I really carry out the gradient. Here, this is the gradient of the Hamiltonian, and since I want the expectation value, I have to take the trace of over the density matrix. So this is the way I calculate, in case your atom may be in a mixture, then this is the way you have to calculate your optical force. Here in this case, we only have, rho is only the density operator for the atomic state. So we only need to take the sum here, J here and here, over all possible atomic states, so 1 and 2, so ground state and excited states. Okay? And now you plug in your Hamiltonian here. So this is the Pauli step-up matrix, and this is Pauli step-down matrix. Here the delta combines omega minus omega 0, so this is the definition of the detuning. And here you have the Rabi frequency, so you have to take the gradient of this term here, multiply it with rho, take the sum over all atomic state, and then you get the force. Okay, now, so this is what I did here. So here I've carried out the derivation. So you have two terms to derive. You have the position dependence of the Rabi frequency omega, but you also have here plane wave component. So this gives you two terms. Okay, the first term is here the gradient of omega, and here you have the gradient of the plane wave. And the gradient of the plane wave is nothing else than h bar k, so the argument of the exponential taken in front. Okay, so we have now two contributions, the upper line and the second line here. Now, as long as we only deal with one atom, we can, without problem, put the atom at the origin, r equals 0. So this simplifies a little bit the terms here. This is what I did here. You see here, I have a sum of some transition matrix element and its complex conjugate. So this is the real part, and the second line is the imaginary part. So you can also write it like this. So, and the transition from 2 via the density operator to 1 is nothing else than rho 1, 2. So the coherence of our two-level system. Okay, times this detunings. So we have here the real part, and here we have the imaginary part. Here we have the gradient of the Rabi frequency, and here we have photonic recoil. Okay, so and now this rho 1, 2 and rho 2, 1 we calculated earlier. Now these are nothing else than this. So we put here simply the stationary solution of the optical Bloch equation. So this equation 274. I click on that just to show you what it looks like. No, this is the solution of the coherences. And this is the formula that I plug in now in the previous formula. And this is what I get. Okay, still two terms. Okay, I have here resonance fractions, Lorentzian type resonance. Denominators go with like a Lorentzian. Here I have still my gradient of the Rabi frequency and the photonic recoil. So and this is basically already the result. Here you have a force which you can derive from a potential, because you have here a gradient. Okay, so you can explain this force as a force as a conservative force, because there exists a potential, and the potential is proportional to the derivative of the Rabi frequency. Here, this is not possible. Here, the second term here has no potential, so it's not a conservative force. This force here we call radiation pressure, and this force we call dipole potential. This force will be used for cooling, and this will be used for trapping. Okay, they are very different. I mean, for example, assume that you have a plane wave. So you have your atom and a plane wave. What would be the first contribution here? Would be 0, no? Because a plane wave has no gradient of the intensity. It's a uniform intensity distribution. So the dipole force would be 0. The gradient of the Rabi frequency disappears. But this contributes. So we have here a force that goes with a photonic recoil momentum. You see another difference here. This force decays very quickly with detuning. So if your laser is on resonance, you will have a very strong contribution from this force. But if the laser is far away, sufficiently far away from your resonance, this will disappear like the detuning over squared. Okay. Here it's different because you have a delta in the denominator and you have a delta squared in the numerator, other way around. So this force decreases with 1 over delta. So it decreases much slower with detuning than the radiation pressure force. That means that if you go away from resonance, this can still contribute while this disappears. And this is good if you want to have conservative trap because then you can put your atom in a potential and it's not influenced by random scattering processes from radiation pressure force. Also, you see that the first force here depends on the sign of delta. So if your delta is positive, blue detuning, then this force will be negative. And if delta is below resonance, if your laser is tuned to the red side of a resonance, it will be positive. So this means that if you have a laser beam, and if this describes the intensity distribution of your laser beam, you can either expel the atom out of the center of the laser beam, if you are blue detuned, or if you are red detuned, you can attract the atom towards the center of the laser beam where the intensity is strongest. And if you have a very nicely focused laser beam, then you can even exert forces on axis, attracting the atoms towards the focus of the laser beam because this is where the intensity of the laser is strongest. Okay. So we can simplify the formula a little bit if we define the optical cross-section, which is done here. So we have a Lorentzian here, and this is the resonant optical cross-section. So this is just the probability that a photon hits an atom or is absorbed by an atom, which is here on resonance. And this is the modification if your laser is detuned a little bit further from resonance. Now here on this formula, this is the dipole force, as I already mentioned. You can write it as a potential. You can write it as a gradient of a potential. Okay, that means that it's a conservative force. And if your detuning is very far from resonance, then you can recover this formula. And this formula you already learned in the first lecture. This is nothing else than the light shift. Yeah, this is the light shift due to the presence of a laser beam. The laser beam shifts your two levels. Then you have two levels. The laser beam, if you shine in the laser beam which is red detuned, then it shifts the levels away from each other. And if you shine in a laser beam, let's say only here, okay, and here's no intensity, but only in the middle here, then you will only have a shift where there is a laser light. And this means that this here is interpreted as a potential. So we can write here VR, here R, and this is the trapping potential. Or if you have another geometry, you have two control by getting laser beam. What does this give you? It's a standing light wave. No? So it's something like this. So you will have you will have intensity maxima and minima. Let's say this is the electric field. Okay. Then here you have no intensity, and here you have maximum intensity. That means your trapping potential will be like yes, the double periodicity, something like this. No? And your atoms can be trapped in the intensity maxima. Now this is for red detuning. If you are blue detuning, it will be just the other way around. So your atoms can only be trapped in the intensity minima. Okay. But there's a problem because if it's just two laser beams, then you will have radial forces also, and the atoms will be expelled radially also by the blue force. So this is why after all, a standing wave made only of 2 laser beams, counterpropagating laser beams, only works really for red detuning. Okay. So let me try to give you a pictorial interpretation of the forces. First of all, yes, the radiation pressure force using the optical cross-section can be written in this way here. So h bar k is the photonic recoil momentum, I over h bar omega. So the intensity over h bar omega, what's that from, what kind of quantity is this? Intensity flux divided by h bar k. It's a photon number, no? So it's a photon flux. So what you have here is h bar k times photon flux times optical cross-section. So it's nothing else than you take a laser beam, you shine it on the atom, and you multiply it with the cross-section of the atom. You multiply it with h bar k, which is the recoil momentum per scattering event, and this is the force. So you can interpret this force here as the photonic recoil times the scattering rate. Okay, so I tried to visualize, to illustrate this here. You have an atom, and you have a laser beam coming here, a photon coming here. So when the atom absorbs the photon, it will receive the recoil of the photon. It will be accelerated to the right. Then after that, the atom can re-emit the light in all directions, isotropically. There's no reason, there's no preferential direction. That means that on average, over many absorption emission cycles, the emission part just vanishes, okay? But it produces a random walk because you cannot say in which direction the photon is emitted and the atom receives the recoil in the other direction, okay? So it makes a kind of a random walk in momentum space, the atom. But this is what happens with radiation pressure. This is the imaginary part of the calculation of the force. Okay, and here I try to illustrate a focused Gaussian laser beam. Now, a Gaussian laser beam has an intensity maximum along the optical axis, and it is stronger in the focus of the laser beam, of course. No? So what happens there? So in a potential picture, you would just say, okay, the atom is trapped along this direction and also along this direction, so it's trapped. Yeah, so this works. But there is also a photonic interpretation of what is happening here. So imagine that since it's not a plane wave, you can expand your focused laser beam in partial waves. So the wave fronts of your laser beams are like this. This is always right angle here. And you can expand this curvature into a superposition of many plane waves. And now what happens here is one photon is taken out of the laser beam, out of a partial wave of the laser beam. Here it's just parallel, but it's emitted a little bit under some angle. So it's emitting light in another partial wave. So basically, you can also interpret the optical dipole force also as the photon absorption and emission processes. Okay, so the atom receives the recoil in this direction upon absorption. When it re-emits the light in this direction, it receives the recoil in the counterpropagating direction, and the sum of this photonic recoil and this photonic recoil, which is written here, gives rise to a force which pulls it towards the intensity maximum, towards the optical axis. Okay, so the dipole force you can always also understand as a coherent redistribution of photons between different laser modes, either partial laser modes or real laser modes. Here, for example, in our standing wave, you can also interpret the dipole force as a coherent redistribution of photons. Imagine that an atom is initially at this position here. So it will receive a force pulling it to the value of the standing wave potential. So you can understand it as a photon absorbed from this laser beam, So it receives a kick in this direction, and it's re-emitted into the counterpropagating laser beam, giving photon the atom momentum kick in the same direction. Okay, so the coherent redistribution of the photon from this laser beam into the counterpropagating laser beam leaves the atom with 2 h bar k momentum. And this we will use very much in the next lecture tomorrow, because this can give rise to a very interesting effect. Okay, so let's see what I have here. So interesting also, you can introducing the saturation parameter, you can also express the dipolar force and the radiation pressure force like this. And you see here that the radiation pressure force saturates. So that means that after a certain amount of time, if you increase the laser intensity more and more and more, at some point you don't get more force, because the force comes from the spontaneous emission of a photon. I mean, before the atom is in the ground state, it cannot reabsorb another photon. So the whole process is limited by the rate of spontaneous emission. This does not hold for the dipole force. So if you increase the dipole force, because here if you let the saturation parameter S go to infinity, that means you have very strong light, very high above saturation. Then this just cancels. This goes to 1. But here you have an S here and you have an S here, and they just cut and they cancel. And this means that by increasing the saturation, you can still get higher on deeper potential and stronger dipolar forces. Okay. Let's see if I can find. Yes, so talking to Pablo the day before yesterday, he asked me what is the physics behind this here. So this is a recipe how to calculate the forces, but you have different degrees of freedom here. No? So you have the external degrees of freedom, you have the light, and you have the internal excitation of the atom. But what is really happening? Why is it possible that the light talks to the center of mass and not only to the electron? Because after all, what you do is with a laser beam, you excite an external transition. No? So an electron goes from one state to another state, but how can this move the center of mass? So I tried to come up with a picture, with an illustration that I prepared here, and I try to explain this now. So assume the physics we can understand easier in a classical way. No? Our brain is made mostly classical, I think. So classical pictures can help you understand better what is really going on. And what is the forces which is exerted by radiation fields is only the Lorentz force, of course. No? So at some point, you have to break it down to a Lorentz force picture. So I tried to visualize it here. I hope you can follow me. So assume you have a static field, electrostatic field, no? Made by two different charges, plus and minus. Okay, and in this field you have an electric dipole. Assume that you have an electric dipole. So, for example, an electric dipole which is oriented in this way. So, since you have a gradient of an electric field, the dipole will experience a force. Okay. So, the force in this case will attract the dipole towards the minus charge, to the bottom, because the atom is actually sitting here in a gradient. So the electric field in the center here is weaker than below, so it will result in a force pulling the atom down. If the electric dipole is the other way around, it will be a force out of the field maximum. Yeah? So radially out, but also in this direction out. Okay, this is for a static field. Now, what happens for an electromagnetic field? For an electromagnetic field, you have a time, in time you have an oscillation of the direction of the electric field, up and down and up and down again. Now, if and this here is now the atom. This is the nucleus and the electron. So below frequency, and then I have to say the Lorentz model consists in assuming that you can describe your atom as a harmonic oscillator. So the electron is bound as like a harmonic oscillator by the nucleus. Okay. Now below resonance, when omega is the frequency of this oscillation and omega 0 is the transition frequency, there is no phase shift between the induced dipole and the electric field. So without electric field, the atom would be neutral and there would be no dipole. But the electric field induces a dipole because the electron is free to move. So, and it is what you see here is the dipole which is induced by the electric field into the atom. Now below resonance, they are in phase, but above resonance, this is a prediction of the harmonic oscillator simply. Okay, there's nothing else than the harmonic oscillator. Above resonance, there is a phase shift of pi. That means above resonance, it's anti-phase. That means here you experience a force which is directed towards the field maximum, and here in the field minimum. Okay, and this is exactly what is happening. So what's happening in the electric field? The atom polarizes and repolarizes very quickly. No? It's an induced dipole moment. And if the field of the driving oscillator of the laser is small in comparison with the eigenfrequency of the harmonic oscillator, then this happens so slowly that the harmonic oscillator can follow, and it will still be in phase, and it will experience a force which takes it to the field maximum, like here. So if this field wouldn't be a plane wave, but spatial intensity distribution, the atoms below resonance are attracted towards the field maximum and above resonance. So this is below resonance, these two cases, and above resonance would be this and this case here. Then it's in antiphase because the harmonic oscillator does simply not have time to follow so quickly the electromagnetic field, and it feels the contrary force. Okay, so this picture. Now I go to. So I think we have now all the tools necessary to use these tools in order to explain cooling and trapping. So this is what I'm going to do next. Applying these forces in order to use them in the lab. So what we really want to do is to take these forces and to cool our sample down to low temperatures. You see here the Bose-Einstein condensation was for many times the final goal. It's the coolest matter in universe. And so basically, if you start in the experiment with a hot atomic beam, for strontium is 500 degrees C or something. So you are about here with the temperature, and simply by laser cooling, we take it down to here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 orders of magnitude on this logarithmic scale. We take it almost like to 10 microkelvin. With strontium, we achieve 1 microkelvin, but the final step to Bose-Einstein condensation, we don't get there. Okay, so this demonstrates the power of laser cooling. And also to give you another idea of the strength of the radiation pressure force. A photon looks like nothing. No? It's, I mean, one photon cooling down some matter is difficult to imagine how this is possible. But in a Zeeman slower, so if you cool atoms down from 700 C to a few millikelvin on a distance which corresponds to 1 meter or so, this corresponds to a force of 100,000 G. Okay, 100,000 times the acceleration of gravity. So it's really a hard wall. Your laser beam, your resonant laser beam, is really nothing soft for an atom. Of course, it's due to the fact that an atom is very light. No? But okay. So yeah, we want to this is the final goal. We want to take the atomic gas down to low temperature. So that you know that every atom is characterized by the de Broglie wavelengths. So this is I have illustrated here the de Broglie wavelengths of an atomic gas above the critical temperature of the Bose-Einstein condensation. So you see that the de Broglie waves do not overlap. So it's a classical thermal gas. They don't interact quantum statistically. So what do you have to do in order to get Bose-Einstein condensation? Well, there's two possibilities. Either you make the atomic gas denser, so in order for the de Broglie wavelengths to overlap, or you make the temperature colder in order to have a longer de Broglie wave. At some point, when this happens, when there is an overlap between the de Broglie wave, then at some point you have to decide whether you are dealing with fermions or with bosons, and whether they want to stick together and form a single macroscopic wave function, or whether they don't like to do that in the case of fermions. Okay, so yeah, this is the de Broglie wavelengths. You calculate it as the Planck's constant over the momentum. Let me introduce already two scales, temperature scales. There's this Doppler limit. I will talk about this a little bit later, which is proportional to the line width of the cooling resonance, gamma. So this is typically 6 megahertz for rubidium, 30 megahertz for strontium. So this is what you can typically achieve with laser cooling. And then there's another typical temperature scale, which is a recoil limit. So this here is the kinetic energy. No? You see here h bar k is p, so it's a momentum. So p squared over 2m is the kinetic energy of an atom. And this is the kinetic energy. So if you use this formula h bar k squared over 2m, then this is the energy the kinetic energy that an atom has after having absorbed a single photon. So let's assume initially your atom is at 0 velocity. It absorbs a single photon, then it achieves some velocity and some kinetic energy, and this is the kinetic energy that it has. So typically, well, this is some, yes, so typically Doppler temperatures are between 1 and 1000 microkelvin, depending on the transition that you use to cool, and below this limit, we often call this temperature ultra cold, below the recoil limit, which is typically on the order of 1 microkelvin. And 1 microkelvin actually is already very close to the temperature that you need for making Bose-Einstein condensation. Okay, so if you have the thermal gas, then the velocity distribution will be according to the Maxwell-Boltzmann distribution. So it's given by this formula. So you have here the Gaussian term here. And this velocity distribution you now can use for calculating the mean velocity in your sample. And the mean velocity is given by this. So the square root of k Boltzmann T over m. This is the mean velocity. And now this mean velocity you now use to calculate the thermal de Broglie wavelengths. So instead of having h bar over p for an individual atom, you take h bar over m times the mean velocity, and then you get the thermal de Broglie wavelengths, which Jörg already introduced in his lectures. Okay. Now, so this is the de Broglie wavelength the mean de Broglie wavelengths of your atom in the sample. Taking this to the squared, you have a volume. And this is, you can interpret this volume as a phase space volume, the minimum phase space volume. If you have more than one particle in this phase space volume, then they need to decide whether there are fermions or bosons. Okay, so quantum statistics comes into play, once you are going to want to put more than one atom in a phase space cell. So what you do is simply you multiply this elementary phase space cell with the density of your sample. You call this the phase space density rho. And if this phase space density rho is larger than 1, then for bosons you have a Bose-Einstein condensate. So this is a condition for Bose-Einstein condensation, not in a homogeneous trap. Okay, so in a harmonic trap there are some corrections to this, but in a box potential this is what you have. Okay, so now here is the critical temperature, which you can derive by this condition. So you set the conditions, okay, I define the critical temperature for Bose-Einstein condensation as that temperature as, where the phase space density is 1. Okay, so I call this Tc. I plug in here the density and the thermal de Broglie wavelength, and I get this condition here. So the critical temperature is proportional to n to the 2/3. So in fact, you could think, yeah, why, if I want to make it my life easier, I want a very high critical temperature. Let's say 1 millikelvin or 1 Kelvin. Why not? All I have to do is to crank up the density. But this is not that easy, unfortunately, because yes. So if I crank up density, I have another problem, because if I have two atoms moving one towards each other, so what I need is elastic collisions to rethermalize my sample. Okay. If I have two atoms, so in the center of mass system of the two atoms, if they collide, they can make an elastic collisions. However, if so they cannot make an inelastic collisions. So what I have to say before is the following: the atomic gas is metastable. This is for a gas. The atomic gas is not the lowest energy state, because for rubidium, for example, it's an alkali metal. The alkali dimers have less energy. So if you take all your atoms in the sample and put them to dimers, you would have a state of less energy. So why don't the atoms do that? They don't do that because if they would do that, they would need to do inelastic collisions. So in the center of mass motion, I can draw the potential like this. So what would be a bound state? A bound state would be, for example, if the two atoms approach each other. Okay, they approach each other and they form, and they go into a vibrational state and they stick together. Okay, and this gains energy to the system because the atoms arrive at this energy. So this is the energy of free particles, and they end up with an energy which is lower. Yeah, so the distance of the vibrational energy to the ionization threshold is the energy that the atom would gain. So, but this energy must be dissipated in a two-body collision. How could you dissipate this? Well, there is actually no way to dissipate this energy. You would need to have some other internal degrees of freedom whose energy would just be this energy here. Kinetic energy is not possible because I've said that in the center of mass frame of the collision, after the collisions there is no kinetic energy left. Okay, so it's basically in a two-body collision it's necessarily elastic. So this process cannot happen. You cannot form automatically from two rubidium atoms. You cannot simply form a molecule. You have some excess energy. And this excess energy must be dissipated in some way. So one way that this energy can be dissipated is a three-body collision. So actually you have another atom which is nearby and which participates in the collision, and the excess energy which is liberated by forming a molecule is given by ejecting one atom with very high kinetic energy out of the trap. Okay. So you have, when this happens, if you have three-body collisions, then you have two loss processes or two mechanisms that remove the atoms from the trap. First of all, you have the rubidium-2 molecules, which are not trapped anymore in the trap because they don't have the same resonance frequencies. And you have the third atom, which also has to leave the trap and which is also lost. So you have a very strong loss mechanism, which kills your atomic gas instantaneously. Oh, these are not optical frequencies here. This is ultra cold collisions. No, this is, really ultra cold collisions. Ultra cold collisions.
And one, but this is like radio frequency or whatever.
Yeah, you would have to have you need a resonance, an internal atomic resonance, which has exactly this the frequency, which would exactly fit. And there's nothing around. There's no internal structure. There's no resonance in the internal structure where the energy could go. What would that be? No? There's only this, and then you have higher excited state potentials, no? Electronically excited state potential. All this can be a little bit more complicated if you have hyperfine structure. Then there is actually a possibility of hyperfine changing collisions and elastic collisions. But in the I simplified a little bit, but basically this is what happens. Yeah. And so you need three-body collisions, but what does that mean? When do three-body collisions come into play? Only at high densities. Okay. So it turns out that three-body collisions play a role if your density is on the order of 10 to the 14th, typically. No? So 10 to the 14th, 10 to the 15 atoms per cubic centimeters, your cloud is so dense that you have a high probability of three atoms to be together, and then your condensate will, or your atomic cloud will explode. And so you are limited in density. So the only thing that you can do is reduce temperature. And if you plug in the density of 10 to the 14th into this formula, you will see that the critical temperature is 100 nanokelvin. Okay. And for a rubidium mass here, put 10 to the 14 per cubic centimeter in this formula, you get 100 nanokelvin. And 100 nanokelvin is typical temperature for Bose-Einstein condensation. This is why it's difficult. And yes, of course, it's difficult to get so low temperature, and you needed technical advances, very powerful technical techniques to be able to cool down the atoms to low temperature. So the first big step was, of course, optical cooling. Yeah, so Philippe got the Nobel Prize for this, Stephen Chu and Courteille in '95. So the first step to understand this is optical molasses. So we don't need to introduce more knowledge or more tools here. We just have to apply what we already learned. So here we use the radiation pressure force. We do not care about the dipolar force. So we go close to resonance, so that where the dipolar, where the radiation pressure force is very strong. Okay, and we take this formula. And now what you do is you take two laser beams. Which are counterpropagating and tuned to the red of an atomic resonance. So you have a detuning from the laser beam to the red of an atomic resonance. Okay. So you have you take this force. Ah, yeah. And what happens then is if an atom is moving. Yes, so if an atom is here, if your atom here is moving with respect to the laser beam, it will experience a Doppler shift. So the frequency will be shifted up or down by an amount corresponding to the Doppler shift. And the Doppler shift can be written like this. So it's let's say this is the z-axis. Then k times the velocity in this axis is the Doppler shift, and it depends on the direction of the motion. So if it's counterpropagating to the laser beam, it will be blue detuned. If it's moving away, it will be red detuned. So you have two forces here, and the sign of the force depends on on the direction of the laser beam because they're counterpropagating, and on the velocity of the atom. So you take this formula and you just change the detuning by this amount. Then you have two forces where you have to calculate F equal to F plus F minus. So you have two times this, you have two of these terms here. And this formula you can now approximate by doing a Taylor expansion for small velocities. So you expand the sum for small velocities Vz, and what you get is this expression. Okay, so you have, of course, your velocity disappears from the denominator here, but it appears there is a linear contribution of this force Vz. And now, if you take this Vz out of the rest of the formula, you can call this alpha d, and you have now a force which is proportional to the velocity, and this is a friction force. Okay, so your radiation pressure force makes nothing else than exerting a friction on the atom. So if the atom is not moving, there will be no forces. Only if the atom is moving, it will experience a force. Okay, so I prepared a plot here, illustrating once more the idea of this red detuning. So if you have only one laser beam now illustrated for one direction of incidence, then if your atom is at rest, then it will be red detuned. So, if your atom moves towards the laser beam, it will be blue detuned. That means it will just make up the initial red detuned and compensate for the red detuning. So here in this case, there will be no scattering or very, very small amount of scattering because the laser is not on resonance and the scattering rate is very low. Here you have very strong scattering, and here you have even less scattering. So that means that the laser only interacts with the atom when it moves against the laser beam. And now, if you have another laser beam coming from the other side, you can make the same direction for the other laser. Okay, so that means that anytime your atom is moving in the direction of the one laser beam, it will scatter photons from this one laser beam, but not from the co-propagating laser beam. Only from the counter-propagating laser beams. That's the idea it's like atoms walking in an optical molasses. So there's only a friction force. There's no trapping term, and in any direction where the atoms likes to move, it receives a decelerating force. And now you can take laser beams not only in two directions, but also in the other direction, and this gives you a three-dimensional optical molasses where you can very quickly cool the atoms to low temperatures. Now here I illustrated this. Of course, your laser beam must be tuned quite close to resonance, otherwise it will make not scattering light. So you need to be sufficiently close to resonance. But then you have here a linear force, so like a Stokes friction or so, which is proportional to the velocity of the atom. So here the atoms are very cooled quickly down to low temperatures. Okay, so people use this technique, and typically this specific techniques you are able to cool the atoms down to temperatures of hundreds of microkelvin or so. But what they finally found is that the atoms were much colder than expected. So normally it's the other way around. No? The theory predicts you idealized system where if everything works fine, then you can reach 100 microkelvin. But this was one example which was where the results of the experiment was much better than predicted by theory. So it took the people sometimes to find out how this happened. And Cohen-Tanuji got the Nobel Prize for explaining this. So the measured temperature were about 10 microkelvins. And this is due to, this is called subdoppler cooling, and it's related to more complicated optical pumping mechanism that I won't explain today. But if you're interested, just have a look at techniques of polarization, gradient cooling, and there are different Sisyphus cooling. There are different techniques, and with this you can cool the atoms to much lower temperature. It doesn't work for all atoms. What you need is a structure of your ground state. So you need a hyperfine structure or Zeeman structure at least of your physical ground state. In strontium, for example, it doesn't work because we have in this atom we only have a single atomic ground state, and there these techniques do not work. So let me come to the magnetic optical trap. This is the main reason why Philippe got the Nobel Prize for demonstrating this for the first time. I think it was invented by Jean Dalibard and Cohen-Tanuji. So the idea is to combine two things. To combine the optical molasses that I've explained just before. So you have a laser beam coming from all directions of space. But additionally now you construct a magnetic field, a quadrupolar magnetic field around the atom. And what this magnetic field does, what I already explained this last lecture, is it makes a Zeeman splitting of your Zeeman levels. So this is a case where your J is 1, so you have three Zeeman states here, -1, 0, and +1. And if since it's a quadrupolar field, the magnetic field is proportional to the distance from the center, so it's linear. So Z is proportional to the magnetic field B. So I can draw it like this. It's linear. Now, what you do is you shine in laser beams in a particular way. You shine in laser beams which are circularly polarized. They are circularly polarized in such a way that they can only make transition between the ground state and some particular Zeeman state. Here, for example, with sigma minus light, you can address the mj equal -1, but you cannot go to mj +1. Okay, so this is a selection rule. You can calculate the Clebsch-Gordon coefficients for the different transitions. The selection rules only allow the transition to this state. Okay, now you choose your direction of incidence in such a way that the sigma minus laser comes from one side and the sigma plus laser from the other side. So this sigma plus laser only couples this magnetic state, and the sigma minus laser couples only the other magnetic state. So what happens now? If the atom is here in the center, it doesn't feel any light forces because the light forces are not resonant to the transitions here. The only points, the only space where this occurs is when the atoms move or drift slowly, let's say, down to this position here, where it suddenly gets in resonance due to the Zeeman shift that it experienced in resonance to one of the laser light. In fact, it gets in resonance to both of the laser light, but this sigma minus laser light is forbidden to make the transition due to selection rules. Okay, so this sigma minus does not couple this transition, only this transition. Okay, so anytime the atom tries to drift out of this region, it gets in resonance with one of the laser lights, and it gets repelled because it feels forces in the counterpropagating direction. Now you do this here in the scheme from all directions of space, and your atomic sample is trapped. And Additionally, to this, you also have the molasses. Now, the optical molasses, remember, is not the trapping potential. The atoms move like in a honey. It's like a small piece of in a very thick, very sticky fluid or so. But it can eventually drift out of the optical molasses. No? Here, not, no? Because here, as soon as it gets, it's a spatially dependent force. As soon as it gets to some area around the center here, it will be repelled. But still, it's the force is radiation pressure, so still it's not a conservative potential. Yeah, it's not. You cannot derive it from potential force. It's a dissipative force because in the same time it does cooling and trapping. So to treat this formally, it's not complicated. You just have to calculate the Zeeman shift, so that the gradient of the magnetic field in space. Since it's linear, you can write it like that. This is the Zeeman shift, which I already introduced last lecture. Now, this is an abbreviation here, and now you take the same formula that I took for optical molasses. Only that additionally to the Doppler shift that I already used for optical molasses, I now have to introduce here a spatially dependent force, which is the Zeeman shift, okay? And now I can make, once again, a Taylor expansion in the position z and the velocity vz, and I get, doing this, I can simplify my formula and it looks like that. So now I have a Taylor expansion with z and z dot. Alpha is still my friction coefficient, but now I have additionally a term which is a repelling force here, which is proportional to the distance. And this is the equation of a harmonic oscillator. Now you can reshape it as a damped harmonic oscillator. The damping corresponds to cooling, but the harmonic oscillator is also a trapped system, so this is what makes which traps the atoms. And you can also, you can then derive and calculate the friction and the spring constant of your harmonic oscillator. Yes, so this magneto-optical trap was extremely successful. So Philippe likes to call it the working horse of atomic physics, because every experiment that we do in cold and ultra-cold atoms starts always with a magneto-optical trap. The many orders of magnitude, 8, 9 orders of magnitude from the hot atomic beam to cold atoms, it's all optical cooling. Here you see, this is our experiment in São Carlos. Here you see a strontium cloud. You can see it with your eyes because it's the light that you shine into the cloud does fluorescence, and this you can see. So if for strontium the transition frequency is 416 nanometers, so it's a nice blue here, and these are 10 to the 6 atoms, roughly at 1 millikelvin temperature. For strontium, there are other transitions with much narrower lines. So this is the transition frequency that you use for cooling this down has a line width of 30 megahertz. But we also have transitions with 10 kilohertz line widths about, and this can take us our temperature down to 1 microkelvin temperature. So just by optical means, just using a magneto-optical trap in strontium, we are able to cool down to 1 microkelvin temperature, which is only a factor of 2 away from Bose-Einstein condensation. Okay, there are other tricks. So I have now to explain you a little bit about radiation trapping. So assume that you have 2 atoms, and one atom is excited. Now, assume that they are initially without motion, so they are at rest. Now, one atom is emitting a photon, and this photon is now, so when it does emit a photon, it receives a momentum kick in backward direction. But then there's another atom which absorbs the emitted photon. So it's after absorption, it's excited. And due to the absorption processes, it's excited in this direction. And what you notice is that the two atoms move away from each other. Okay. So the exchange of photons results in an increase of the relative motion of the atoms. So if you imagine now that you have your atomic cloud, which is extremely dense, which is at low temperature, imagine that it's a Bose-Einstein condensate. Now you let the photon go in. What does a photon do? If the optical density is very high, then it will be absorbed. It will re-emitted, reabsorbed, re-emitted, reabsorbed. So it makes a random walk in your cloud. And every time it does so, it will push away two atoms from each other. And that means that the density goes up. So the atoms tend to move away from each other. The density goes up. The density goes lower. I mean, the size goes up, but the density is reduced. And this is not what you want for Bose-Einstein condensation, because you want that the atoms stick together. No? Remember that the phase-space density is n times the summary, the Broglie wavelengths to the third. Now, if you increase n, you have more difficulties in getting to high phase-space densities. Okay, so this phenomenon is called radiation trapping, and always occurs if the density of your sample is very high. So the sun, for example, is a very high density gas, and if you put a single photon, let's say, in the center of the sun, it takes 4,000 years for the photon to find its way out, due to this processes. Absorption, re-emission absorption. So it takes some amount of time. The characteristic quantity that determines whether you are subject to radiation trapping is of course the optical density. So if the probability for a single passage of a photon through the atomic cloud is large, then you are subject to radiation trapping. And this is the reason why it is impossible, until now, it has not been possible to make a Bose-Einstein condensate with optical cooling means. So you need another idea, another technique where photons are kept away from your atoms. So, and this brings me to the other technique of evaporative cooling. Did I put this? Yeah, here. Okay. So let me do this qualitatively. When you have a thermal gas, then you have your thermal gas will be the energy distribution will follow Maxwell-Boltzmann distribution, like this here. So this is the energy distribution of a thermal atomic gas in your trap. Now, if you imagine your atomic cloud is trapped within a trapping potential. So if the trapping potential is very deep here, you can trap an atomic gas with pretty high temperature. Okay. Now, if you're what the atoms do inside this trapping potential, they oscillate back and forth. Yeah. If they don't, assuming that they don't do too many collisions, then a single atom has the possibility to convert kinetic and potential energy. So the hottest atom, there will have a probability to go very high in the potential. And if you now managed to limit your potential, so that atoms which are coming to this position, imagine that this is a direction of space, they are expelled from the trap. They can just leave the trap. That means that all atoms which are be above this limit, they can actually leave. Okay. I already mentioned this in a previous lecture. And what you do is by truncating this distribution is nothing else than what I've illustrated here. You take all the atoms which have an energy which is above some certain limit. You just take them away. So you truncate your Boltzmann distribution, and you're left with a distribution which looks like this. Here's truncated. Okay. Now, if you don't do more than if the atoms can rethermalize, so if you have some rethermalization mechanism, what they will try to do is they will try to form a new Boltzmann distribution, which is characteristic for the thermal equilibrium. Okay. So, but in order to do so, you need elastic collisions, yeah? Because you have to redistribute the kinetic energy among the atoms in such a way that they are equilibrated. And it takes, on average, 3 collisions per atom to equilibrate a sample. So every atom has to undergo 3 elastic collisions. This is just the house number, no? In order to leave your sample after that in a Boltzmann distribution to which you can attribute a temperature. Okay, so temperature, the notion of temperature makes only sense when you are in thermal equilibrium. No? So you need elastic collisions to do that, and yeah, I don't walk you through the calculations. Yeah, this is what I wanted to show you. Basically, you can calculate this. You know, you have to calculate your distribution. So this is the number of atoms you have to introduce to calculate the state density for your trap. It depends on the shape of your trap. So for harmonic trap, you have this expression here, which you have to calculate in order to calculate to relate the numbers of atoms with the energy. Okay. And here is the energy. And the energy, if you carry out the calculation, the energy is in equilibrium is given by 3 times the numbers of atoms times the Boltzmann constant and the temperature. Okay. So after your truncation of the Boltzmann distribution, yeah, you have less atoms. Of course, you have to sacrifice some atoms. And you, after the rethermalization, you have a new temperature that you can define by that. And now, what you can do in order to understand the simulation. So you start from this distribution. After thermalization, you have a Boltzmann distribution which is peaked at a slightly lower temperature here, and it's going. It develops a new Boltzmann tail, let's say. A high-energy Boltzmann tail at here, which you can now truncate once more by lowering your potential barrier. Where the atoms are spilled out here, and you do this over and over again. But the conditions to be able to do that is elastic collisions. Yeah? So you need lots of elastic collisions, and this is actually the most difficult part of making cold atoms, that you have to guarantee that your atomic cloud is sufficiently dense that you have a lot of elastic collisions. Because this is not obvious. So basically, if you start always with a magneto-optical trap. If your initial density is high enough, then you can go to runaway evaporation. If your initial density is not high enough, then you start truncating your Boltzmann distribution more and more and more. But since you don't convert your initial distribution, it basically stays the same shape here. You just cut into this distribution here instead of having equilibrium temperature, which is at lower and lower temperatures. Okay. So I made here small simulations that you can download here. And if you plot now the numbers of atoms, so that means the integral of under this Boltzmann distribution, and the energy, that means the peak of this of the maximum of this Boltzmann distribution, against each other, you get a curve like this. And this curve, so this curve here, the upper curve corresponds to 10 to the 9 atoms at 100 microkelvin temperature. This is typically where you start evaporation. And then by cutting more and more down here the atomic cloud, you sacrifice a lot of atom, but you also get lower in temperature. And here you see that it's not very advantageous because you lose, in order to get to the threshold that might be around here, so you lose 6 orders of magnitude of atoms in order to get 2 orders of magnitude of temperature down. So it's really a big sacrifice of all those atoms in order to get very few atoms down to very low temperatures. If you do it right, that means that your temperature gets lower. If your temperature gets lower, that means also that the atomic cloud will start to concentrate in the center. So instead of being dilute here, when you get to lower temperature, it will pile up in the center, and it will actually increase the density. And increasing the density means increasing the collision rate. So you need to get on a slope where while cooling down here, you also increase the density. If you don't have enough collisions, then this density will not increase, and at some point you reduce your collision rate because you sacrifice so many atoms that the density in the center is actually going down. Okay. So this is the technical challenge to. Actually, the problem is that you have to fight against other loss processes. In a magneto-optical trap experiment, you need to do this in an ultra-high vacuum chamber. No? Actually, we call it XUHV, which is extreme ultra-high vacuum. So this is the best vacuum that the technology nowadays can do. And this is typically, well, the best experiments can take you down to 10 to the minus 12 millibar. That means that you still have atoms in the background gas, which can collide with your atoms in the trap and transfer kinetic energy to the trap and expel them. And at 10 to the minus 12 millibar, the typical lifetime of a Bose-Einstein condensate would be, I don't know, 30 seconds or something. So within 30 seconds, you can do a lot of experiments, of course. No? But it's just to give you an order of an idea of the challenges, because the whole ramp here also takes 30 seconds. So typically, in typical experiment, ramping down, because you cannot cut down, lower down your threshold here faster than the rethermalization rate. And if you only have remember that you need 3 collisions. If your collision rate is smaller than 3 collisions in a given time, then you have to wait to rethermalization before you can put your knife down to a lower position. And the velocity at which you can do it is given by the ultra-high, by the vacuum, by the quality of your vacuum. So if you have a very good vacuum, you can do it slowly. Then you can take your time and leave enough time for the atoms to rethermalize. If your atom is bad, if your vacuum is bad, then you have to ramp down quickly, because if you ramp down faster, if you ramp down slowly than the losses, then at some point you end up in the condensate with no atom. Yeah. So, or with 1 atom. And so this is the condition to get the Bose-Einstein condensation. Okay. Let's see what So I have 15 minutes. I wanted to give you an example of optical dipole trap. So here I illustrated the potential shape in 2 dimensions of a Gaussian laser beam. So a Gaussian laser beam coming from this side. Now, if it's strongly focused, you will have a strong radial confinement here. And a Gaussian laser beam, this is, all lasers have Gaussian shapes. So this is a typical situation. And you have also potential in axial direction, which is given by the focus. This is a standing wave laser beam, so 2 contrapropagating laser beams, and you can put your atoms inside this sides, this small potentials here. You can actually do it for 1, 2, 3 dimensions. No? This is for 1 dimension. You can also have laser beams in 3 dimensions, and in 2 dimensions, 3 dimensions. In 3 dimensions, you can visualize it as an how to say. A potential where you can put X in. Let's see how to draw it. Well, it's a 3-dimensional cubic lattice. Okay, so you can have a 3-dimensional cubic lattice where in every side you put in a certain numbers of atoms. And you can actually do solid state physics because since it's already a crystal, you can study features which are common to crystals. Now let me show here you the formula of a Gaussian laser beam, because this is what you typically have. So this is a Gaussian laser beam. So it's you have the power of the beam. W0 is the waist. So laser beam typically looks like this. This is the waist. That means the diameter is the smallest at the smallest point at the focus. It's called the waist. So it's a Gaussian here, and in the z direction. So z, x, y. In z direction, it's given by the Rayleigh length. Okay, the Rayleigh length is defined like this. No? So this is typical intensity distribution that you can plug into the dipolar force that I've showed you before. No? Now you can take 2 laser beams which are contrapropagating, or you can, what we do in the Strontium experiments, you can take 2 laser beams like this. Because actually in this direction, the confinement is very strong because the size of the focused laser beam, the radial size of the focused laser beam is very small. And in this direction, you can also make it very strongly confined in a very small laser beam. And if you cross the 2 laser beams, then you will have a very strong confinement potential in the center here. Okay. And you can really have very small and very, very steep traps to make very high densities with your atomic clouds. So at the end of this lecture, I wanted to give you an idea of how we measure these cold gases. Here. So basically, what you in order to gather information from the atomic cloud or the Bose-Einstein condensate, you have to take pictures of it. No? But how do you do this? Okay, so imagine you have your atomic cloud here, and what you do is to shine in a plane wave laser beam, so the plane wave laser beam will interact with your atomic cloud, and it can make 2 things. It it can absorb photons. So photons can be absorbed by atoms here and scattered away. These photons, of course, they are missing in the transmission. So what you do actually is you imprint a shadow in your laser beam, and this shadow you image on a CCD camera. So this is how it's done. Of course, the laser beam here, the frequency of the laser beam must be in resonance with the atomic transition. So if you're have an atomic transition, then it must be on resonance. But another thing that can happen is the light can be shifted, phase shifted by the refraction index produced by the atomic cloud, and this can lead to a deformation of your phase profile of the laser beam. And there are also techniques to use this for imaging atomic clouds. Only that are a little bit more sophisticated, and they work if the frequency, if your laser is not on resonance, because the refraction index of your atomic cloud is 0 on resonance. It's 1 on resonance, but it can be different from 1, so smaller or larger than 1, below or above resonance. Okay, and this if you want actually to irradiate a laser which is on resonance, if the laser is not exactly on resonance, then you will additionally to having this absorption process, you will have also a deformation of your phase front, and this deformation leads also to a focusing. Okay, so if you have, for example, a deformation, a retardation of your phase front, it leads to a focus of your laser beam, and this can falsify the information that you would extract. For example, you want assume that you want to measure the size of your sample. Okay. If you don't hit the resonance exactly, if you are a little bit above or below resonance, then you have a focusing or defocusing, and then you measure here a smaller size than you would have had on resonance, and this gives you a wrong information about the density of your cloud. Okay. And yes, this is very important. And here I've written down the formula. So you have the absorption that I mentioned here is given by the local density and the cross section. The phase shift is the absorption basically times this fraction. Yeah? So the detuning over gamma. So if you walk a laser beam, an electrical field of your laser beam through resonance, you will have the term, so the phase shift simply due to the distance. Okay, so this is without atoms you would have this exponential. With atoms you may have absorption, so this is a real exponent, and here it's an imaginary exponent containing the phase shift. Now, plugging in these expressions here into this formula, you get this here. Now, I've assumed here that the density of your atomic cloud is non-homogeneous. What you then have to do is you take the integral of the column integral of the density distribution of your atomic cloud. So the integral of the density distribution, I could draw it here, the density distribution along the z-axis could be, for example, a Gaussian, if it's in a thermal cloud in a trap. So the density distribution here would be a Gaussian distribution, and I have to integrate over this to get the optical density. Okay. So this is the formula that I give. If I take this to the squared, I get the Lambert-Beer law, which many of you may know. So if I assume that I'm on resonance, so I take this delta to 0, and here I have the resonant optical cross section, then I have here an expression E over the input density intensity, and this is exactly what we look at. So we have an intensity E as a function of x and y, so x and y, and z is in this direction. No? So these, we cannot see Z, but we can see the density distribution of the cloud in X and Y direction. Okay. So so this E as a function of X and Y over E naught. And then we multiply it with a column integrated density distribution. And so it's equal to E to the minus alpha, which is also a function of X and Y. Okay. And so this is what we see on the CCD camera. So the intensity distribution of the laser beam having passed the atomic cloud, normalized to the incident laser intensity. And this is what we infer. So we take the logarithm of this. This gives us the optical density. And from the optical density is here, we can infer the atomic density in X and Y direction. So we know how we know this size here, and we also know the numbers of atoms because we can integrate the whole picture in X and Y. And from the depth of the laser, from the depth of the transmitted intensity at the maximum, we can calculate the maximum density N naught, and basically from this is the way we extract all information that we have about thermal clouds or condensates. This is the only thing that basically we can do really, taking pictures. And here I show you pictures, typical pictures of what we. So this is what I explained here. No? So we infer the density distribution, the density distribution in X and Y, which is not integrated here, from the optical density that we measure. And this is how we do it in practice. So we have a trap. So for example, a magnetic trap or the dipolar trap. So we cannot use a mod. Well, yes, if we use a mod, then we don't have a condensate. But yes, any trap here. Assume that you have here a mixture of a thermal cloud and a condensate. So the thermal cloud I illustrate here by many atoms which are green here and which are not degenerate. So there are many small circuits here, and they are elliptical here because I assume that the trap is elliptical. Many traps there are harmonic, but not necessarily isotropic. Okay, so the atoms are more compressed in one direction than in the other direction. That means that every atom here, described by a wave function, is more compressed in one direction than in the other direction. And this also holds for the Bose-Einstein condensate, which is more compressed in one direction than in the other direction. Now, what happens if you now this cloud here is very dense. It's so dense that you cannot get a laser beam through. And if you cannot get a laser beam through, then you have no information about the spatial density distribution. So it's opaque. Okay. So the typical optical density of a condensate is thousands. So that means that really you pump photons in your condensate, and they will be scattered many times. They will destroy the condensate before you have a chance to get some information out of the condensate. Okay, so what we need to do is we have to reduce the density of the cloud, and this we do by letting the cloud expand ballistically. So we suddenly switch off the magnetic trap. Then the condensate and the thermal atoms, they fall by gravity down, but they also expand due to their residual temperature. Okay? And also due to the kinetic pressure, because if initially a wave function is very compressed, if you start letting it go, it will disperse quickly if it was initially very, very confined. So this is just normal dispersion of a wave function. So in the direction where it was initially more constrained, it will start to expand faster, and both will do so, the thermal atoms, but also the condensate. Only that since the thermal atoms are individual, they will also every atom by itself will expand its wave function now from horizontal to vertical, but the whole distribution will remain round. Okay. This is not the case for Bose-Einstein condensate, which is described by a single wave function. So it just flips its asymmetry from one direction to the other direction. And this is how you can identify a condensate, because it changes the aspect ratio while the thermal cloud does not. Yeah, and then after typically a few milliseconds, you shine in the probe laser beam on resonance, and it makes a shadow in your laser beam, and the shadow you image on the CCD camera, and then you run your programs in order to analyze what you saw. And here I show you the experiments, the measurements that we have taken. I think it was 97 in Austin. So this was 2 years after the big first 3 condensates, so Eric Cornell, Ketterle, and Randy Hewlett. We managed to do a Bose-Einstein condensate at the University of Austin in Texas. And this is what you see. So above the critical temperature, you see a thermal cloud, and not much more. Then you cool down. You already see that this curve is not Gaussian anymore. So it actually has a bimodal distribution. Here you can see this is below threshold temperatures. Here you see a condensate appearing, and this here, the outer side here is described by a Gaussian curve which fits to the thermal part of your cloud, and on top of that you have a smaller, more compressed distribution, which is the Bose-Einstein condensate. And this is what I showed here. Your thermal cloud will expand faster and wider than the remaining part of your condensate. So yeah, you make a fit of the density distribution of your thermal cloud, so the green atoms. And from this you had extracted the temperature, the equilibrium temperature, assuming that there is an equilibrium temperature between the condensate and the thermal cloud. And on top of that, you have the Bose-Einstein condensation. Okay, so I'm at the end of my time. Yes, just the final comment that I wanted to do here is the following. So we have seen here that we have 3 degrees of freedom. We have the center of mass motion, we have the light, and we have the internal degrees of freedom of the atom. So in the first lecture, I showed you that there is a light shift, which shifts. So if you shine a laser beam into your thermal cloud, then the atoms, the internal degrees of freedom will suffer a light shift. Okay. Then I told you that the external degrees of freedom, the center of mass motion, is subject to a dipolar force. This dipolar force you can yeah, or maybe I should just take the pictures which are already there. So assume this. So this is a light shift here, but if you interpret this as a potential, as I already explained to you, now take the Broglie wavelength, which is oscillating. When the atom now is entering in the potential, it's accelerated. When it's accelerated, it means that its velocity is faster. When its velocity is faster, it means that the Broglie wavelength goes down. So it makes some oscillations here, some fast oscillations, while it is in the center of the potential, but it has to go out of the potential anymore after that, and then it will reduce its oscillation frequency. So while it is in the potential, the Broglie wavelength is faster. Now this is exactly what Jörg told you when showing the wave functions of 2 colliding atoms. When the approach is when they're very far from each other, they are doing very small oscillations, very slow oscillations. When they approach each other, they make some very fast oscillations until they meet the inner turning point, and then they go back. And this is the same thing, only that here you have one single atom in an external potential. Okay? So you have here the Broglie phase shift. And now the last 10 minutes, I explained to you that the laser beam can also be phase shifted. This is the phase shift data. So if you have a laser beam coming into the atomic cloud, due to the refraction index, if the refraction index is not 1, but it's 1.5, for example, then what you have is your phase fronts are closer to each other. And this corresponds to so it's not a de Broglie wave here, but it should be the laser phase. I have to correct this. So the laser phase now here, if the refraction index is larger, it will be compressed. And all these phase shifts are the same. They are not entangled. They're intricate, so they're coupled. If you calculate the phase shift of your Bloch vector for the inner state, you calculate the phase shift of your light beam entering through the atomic cloud, and you calculate the phase shift of the de Broglie wavelengths. They are all calculated in the same manner. Yeah. So all the degrees of freedom, they suffer this phase shift in the same way. Okay, that's all. And so next lecture tomorrow, I will use the notions that we have acquired so far about atoms interacting with light to tell you about an experiment that we're trying to do in San Carlos, and which has to do with Bloch oscillations of atoms in a standing laser field. So two counterpropagating waves makes a standing laser field, and the atoms can undergo Bloch oscillations in this standing wave. And I will also tell you about cooperative effects, so spontaneous synchronization of atoms and of light interacting with each other within an optical ring cavity. The optical ring cavity that I showed you on the picture where you saw the strontium mod, there was actually a nice cavity, and this is a cavity which we want to use to make. Where is it? Here. Show it because it's so nice. So here you see three mirrors. Here, here, and here. There is an atomic cloud in the center, and we want to have the atoms interact with this cavity and see what's coming out then. So this I will tell you tomorrow. Are there any questions?
So you cannot directly measure the temperature of the cloud. You infer it by measuring the density, or how do you know that it's microkelvin?
Yes. So this is the picture that I showed you here. Yeah, maybe it's easiest seen here. So here, your initial cloud has a velocity distribution, and so every atom has a mean velocity, let's say. And if this mean velocity is large, then the cloud will expand much faster. So from this radius of this cloud, of the thermal part of the cloud, we can infer the temperature. Not of the condensate, because the condensate itself, the shape is determined by the initial trapping conditions. So if you have a trap which is like elliptical, then the condensate will also adopt this elliptical shape. And when you now let the condensate expand, it will expand in the contrary direction. So an initially elliptical shape like that will revert its aspect ratio. But this expansion does not depend on the temperature. It depends on the initial trapping conditions. So if it was initially very strongly confined in one direction, this is due to the fact that the atoms interact with each other. So they try to, for example, repel each other if you have a positive scattering length. So if you against this repelling force, you try to compress them. Once you release them, they will explode in this direction. So this has nothing to do with the temperature, and you can only use the thermal cloud to infer the temperature. So in this distribution that you see here, Oh, sorry. Here you can only, you have to do a bimodal fit. That means you can only fit the circular part, because you know that the circular part is from a thermal cloud. And you cannot, here it doesn't work, no, because it's elliptical. So here it does work. But here, I mean, this you do numerically. You still have to find, to fit a bimodal density distribution. That means, if possible, a two-dimensional circular Gaussian to fit this thermal cloud, which is below here. And additionally, an elliptical distribution, which fits the inner part here. So these are the very first pictures. So nowadays they do much nicer pictures, but I chose this picture for historical reasons, and since we did this ourselves. Yeah, and the total numbers of atoms you just integrate under this. You know? And then you can trace the interesting information, like the numbers of atoms in the condensed part, divided by the numbers of atoms in the non-condensed part. So you can infer NC, so the numbers of condensed atom, the total numbers of atom, and then you can plot this. I mean, there's a theoretical curve which I think goes like this. I don't remember, it's to the third power or to the third half. Depends on whether it's harmonically trapped or in a homogeneous potential. But something like that. And then you see this typical plots, like below the critical temperature here. You get a macroscopic population in the condensed fraction. So here you plot T over Tc, let's say, then this is 1. And then this would be, yeah, N. No, 1. Yes, and then I didn't identify this critical temperature and compare this to the calculations. The critical temperature depends very much on your conditions. You know? If you have a very compressed trap, then the critical temperature goes up. So it's easier to get to Bose-Einstein condensation in a very compressed trap, because then you don't have to cool that much to low temperatures. More questions? Okay.